Very good morning, students. Today we will learn about the oscillations. This is the second module of your syllabus, oscillations, in which we will cover simple harmonic motion, damped oscillations, and its mathematical analysis, as well as we will see the forced oscillations and resonance. So one by one, we will be discussing all these aspects. But first of all, we will start the introduction of simple harmonic motion, how it actually takes in a particular environment, and how we can have an idea about the energy, velocity, acceleration, and different examples of simple harmonic motion. Then we will apply this knowledge to understand the concept of damping, and then the forced oscillations, and then resonance. So one by one we will start. So let me share my screen first, and then we will start once. Hope my screen is visible to you, and we'll be sharing. We will be discussing the module 2 oscillations part 1, in which we will start learning introduction to simple harmonic motion. And we will start with a very small definition of simple harmonic motion, as you can understand that how it will work. So oscillations will comprise of simple harmonic motion, damped oscillations and its mathematical analysis, then forced oscillations and mathematical analysis, and then later we will discuss resonance. So one by one, all these parts we will try to learn. So, but first we will start with the entire discussion, entire introduction with examples, numericals, and how we can use simple harmonic motion in day-to-day life, and how it can be analyzed in a proper manner. So that we will learn. So myself, Dr. Pradeep Sharma from University of Engineering and Management. You can note down my contact details from here. In case of any problem, you can directly contact me and directly write to me if you want to for any discussion regarding any problem or any topic. So these are the parts we will learn: free vibration, forced vibration, and resonance. But here, mathematical treatment of damped vibration, time constant or modulus of decay, energy relation, evaluation of alpha and omega naught, logarithmic decrement, and then mathematical treatment of forced vibration, velocity expression in steady state, resonance, power in forced vibration and resonance, and then work done against retarding force and sharpness of resonance. So all these topics we'll learn, but we'll start our topic of today's discussion with simple harmonic motion. What actually it is? So if you go by the definition, it's very simple. That is such a motion in which acceleration is directly proportional to the displacement and is directed towards the mean position. It's called simple harmonic motion. So from the definition, I hope it's difficult to understand what actually it is saying. But when you will see this, so I think it's very much understood by this diagram that if at any point, this is the equilibrium position around which it is taking the equal amount of displacement in both the directions. Kindly see this: when this position, blue color position, is increased, restoring force works in opposite direction. So you can understand that the force which actually governs its displacement about the equilibrium position is directly proportional to the opposite of the position, opposite of the displacement. So you can understand this example because the spring is actually working, and if that spring is providing the force, so once it is providing the force in opposite direction, and another, see here, So when the string is compressed, it is providing the force in the direction so that the block can move towards the equilibrium position. But when it is away from the equilibrium position, when the spring is stressed, then the spring makes a force oppositely, again bringing back the block up to the equilibrium position. So this restoring force is you can say proportional to the displacement, but in the negative direction. So we can analyze like this. This is the equilibrium position, the mean position we say. Suppose it is at x is equal to 0, and when it is at the last position here, it is at x distance, and again when it is at this position, again it is at x distance. So this force, when it is in this direction here, when the spring is compressed, is towards the mean position, and again when this block is away from this mean position, the restoring force is again towards the mean position. So you can understand that the restoring force is always working towards the mean position, and basically it is trying to restore the position of the block at the equilibrium position. Okay, so we can understand that in here acceleration is directly proportional to the displacement. So force is actually providing the acceleration to this block, that is MA, and it is directly proportional to that displacement. So A is directly proportional to X. So if we can have a spring system in the same arrangement like this, see. So from both the sides, there are two springs and a single block is being confined within that. So this is the mean position, you can understand, and when it is away, then both the springs are actually working. One is working to make this block again at this position, and the compressed spring is making a force in this direction. So that way the motion of this block actually takes place here and there, to and fro motion like that. And again it is repeating its position at the mean position after some period of time. When we see the simple pendulum, because it's a simple pendulum is the best example to understand the simple harmonic motion. So we can understand that if a bob is there attached to a string, there are certain properties with the string, like it should be massless, it should be inextensible. So if that kind of string is there and for mass is being rotated like that, so you can understand that when it is at the extreme position here is the maximum displacement from the mean position. This is called the amplitude. Okay, and the restoring force, this F, is working towards the mean position. It is working actually to bring this bob towards mean position, and the weight of the bob is working downward, and the tension on the string is working towards the point of joint. Okay, so the component of this weight which is working towards the F, that will be actually our restoring force. Okay, so we'll try to understand more of this, but I think now you can understand that what type of motion we are talking about and how we will analyze it one by one. So conditions for SHM, simple harmonic motions, now we can define very easily, like the system should have the restoring force, the system should have inertia, and the system should be frictionless, because no opposite force should be there, because otherwise it will create the damping, and after some time this oscillation will fall off and this oscillation will die. So this is the important law, as already we have in one of my previous lecture we have discussed this Hooke's law. which actually governs that the property of elasticity. And we say that the force that is applied to that spring is directly proportional to the displacement. And if the spring is unstressed, there is no net force on the mass. And if the mass is displaced from the equilibrium, then the spring will experience a restoring force, which is directly proportional to the displacement from the equilibrium position. And F is equal to Kx, where K is the spring constant and F is elastic force and F is displacement by applying that force. So this is a simple notion of the Hooke's law we will apply, and this is the restoring force in a spring system. Now, expression for acceleration, if we can have, we can easily find out that F is equal to minus Kx. So we can make out that in this system, the restoring force is written as F is equal to minus Kx. Due to this restoring force, acceleration is generated into the system, and that's why we can have an expression F is equal to mx double, which is actually expressing the acceleration of the system. So this way we will be analyzing proper system. And because these two equations F is equal to minus Ks and F is equal to mx double dot, basically representing the same force. This is due to the spring and this is the result, and there is no loss because the damping is not there and no opposite force is available to restrain this motion. So these two will be equal. So if we compare these two, so mx dot is equal to minus kx, and we can get that acceleration is equal to minus k by mx, where k by m is constant and acceleration is proportional to displacement. That is the primary condition of our discussion for SHM. So we can have that x double dot plus k by mx is equal to 0, and solution is of the form of x is equal to a cos omega t plus phi, where omega is k under root k by m. So this equation actually corresponds to the general equation of a wave, and we can easily find out that omega is under root k by m. So this way, one by one, we can sort out, and omega is the angular frequency, and accordingly we can find the linear frequency and time period of the system, which is being under simple harmonic motion. And we can easily get the velocity if we have the x value, the displacement. We can have the velocity by differentiating. So v is equal to minus a omega sine omega t plus phi. Again, we differentiate with it with respect to t. We can find the acceleration. A is equal to minus a omega square cos omega t plus phi. So if you see here, a and cos omega t plus phi, this is the value of x. So we can put a is equal to minus omega square x, right? So this omega square value, we can put acceleration in this form. At is equal to minus 2 pi s square xt, because omega is 2 pi s. So that way we can easily find it. So this way we can find the values of the system, and let me explain you one thing, that here this part a is equal to minus omega square x, we can have in relation to this, okay, or this. A is equal to minus k by m x. So a is equal to omega square minus omega square x. It means omega square is equal to k by m, or omega is equal to under root k by m. So from this relation, from these two relations, and from the relation of this a is equal to minus omega square x, we can find that omega square is equal to A by M, and we can find this solution. Okay, so using this and using that omega is actually equal to 2 pi divided by capital T time period. So we can find out from here time period also. Okay, so the time period of the system easily we can find out. So thank you. We will be learning how to analyze the simple harmonic motion in the next class. We'll try to see how SHM in different systems will work and how it can be analyzed for we can understand for energy part, for displacement, velocity and acceleration part. Thank you. Thanks a lot.